Okay, so we're back on. So we showed that if the sum of two invertible matrices not necessarily gives an invertible matrix, and this matrix here is non-invertible because the determinant is just 1 times 1 minus 1 times 1, and the determinant is, that means that it's 0, which means this matrix is non-invertible. And 3, this is also not closed under scalar multiplication. Here we have to be a little bit, this is a little bit tricky. Why? Because when we are proving a scalar multiplication, that means that C times any matrix from this set has to stay in this set. So if I take any invertible matrix and I multiply it by any constant, by any real number, okay, the product, what I'm going to get, it is still going to be invertible. But this is very important for any constant. Well, that is not going to work if you take the constant 0. So 0 times 1, 0, 0, 1 gives me just the 0 matrix. And that's non-invertible, right? So this is an invertible matrix, and I'm multiplying it by 0, which gives me the 0 matrix, and we know that the 0 matrix is non-invertible. So that means that S12 is also not closed under scalar multiplication. And here we show that S12 is not closed under vector addition. It's needless to say that this is not a vector space where none of the conditions are satisfied. And S13 finally, so I have the set of 2 by 3 matrices, so that means A, B, C, D, E, F times 1, 1, 2, 2. Well, let's calculate this product. This is 1 times A plus 1 times D, that's A plus D, B plus E, C plus F, and then 2A plus 2D, 2B plus 2E, and 2C plus 2F. And this has to be equal to the 0 matrix in the vector space of matrices 2 by 3, so 0, 0, 0, 0, 0, 0. We compare each corresponding entry, so A plus D is equal to 0, B plus E is equal to 0, C plus F is equal to 0, and 2A plus 2D is equal to 0, 2B plus 2E is equal to 0, and 2C plus 2F is equal to 0. These are the same conditions as you can see, so from here A is equal to negative D, B is equal to negative E, and C is equal to negative F. That means that my matrix A, B, C, D, E, F basically is A, B, C, negative A, negative B, negative C, which is A times 1, negative 1, 0, 0, 0, 0, plus B, 0, 1, 0, 0, negative 1, 0, plus C, 0, 0, 1, 0, 0, negative 1. Since S13 can be expressed as a span of vectors in M2 by 3, that makes it S13 a subspace. And the basis is going to be consist of these 3 terms, which means that its dimension is 3. Okay, and the second question on this worksheet is determining whether these sets are whether the following sets are linearly dependent or independent, and then I told you how to proceed here. When you have polynomials, you can just create a matrix consisted, each column is going to represent the coefficients in the polynomial, so negative 1, 2, 3, 4, then 3, negative 1, 2, negative 1, 3, -1, 2, -1, and finally 11, 3, 22, and 11. And now we row reduce this. So that's 1, 3, 11, 2, 3, 4, -1, 3, 2, 22, and -1, 11. These polynomials are going to be independent if these columns are independent, and these columns will be independent if I have pivot in each column, right? So 1, 3, 11, 2 minus 2, 0, -2 minus 6, -7, 3 minus 22 is -19, 3 minus 3 is 0, 2 minus 2 minus 9, -7, and then 22 minus 33 is how much? Negative 11. Hope I'm not making some big mistake. And then 4 minus 4 is 0, -1 minus 12 is minus 13, and then 11 minus 44 is minus 33. Okay, so let me just make sure that this is right. So this is row 2 minus 2 times row 1. And then row 3 minus 3 times row 1. 2 minus 9, -7, and 22. Okay, so I can multiply all of these by 1. So 1, 3, 11, 0, 7, 19, 0, 0, 11 minus 19 is -8. And then row 4 minus 13 over 7, row 2, so 0, 0, and then 33 minus 13 times 19 over 7, which gives me, well, whatever it gives me, whatever number it gives me, I can see that I will not get a, oh no, sorry. So I get 3 pivots. So I get 3 pivots, which means that these polynomials are linearly independent. They are linearly independent, which I don't have in my solution, so obviously I made somewhere a mistake. So you try to calculate this one more time. Oh, that's the mistake. So when I multiply the first row by -1, this is negative and this is negative. So scratch this. Sorry about that. So 1, -3, and -11. 2 minus 2, 0. So I'm using this operation. -1 plus 6 is 5, and then 3 plus 22 is 25. Now row 3 minus 3 is 0. 2 plus 9 is 11, right? And 22 plus 33 is 55. minus 4 times 0, 1. Negative 1 plus 12. It's 11, and then 11 plus 44 is 55. Okay, obviously I have these two rows are the same, so when we're going to cancel them, I get 0, 0, 0. At the bottom, 0, I can divide this by 11, 1, 5. And I can divide this one by 5, and I get 0, 1, 5, 1, negative 3, negative 11. Because these two rows are the same, I get 1, negative 3, negative 11, 0, 1, 5, 0, 0, 0, 0, 0, 0. And hence I don't have a pivot in each column, which means that these polynomials are linearly dependent. Linearly dependent, which means that the basis, moreover, this matrix tells me what polynomials are independent. I have pivot in the first two columns that correspond to the first two polynomials. So the basis is consisted, the basis for the span of S1 of this set is negative 1 plus 2x plus 3x squared plus 4x cubed, and 3 minus x plus 2x squared minus x cubed. So I take the first two polynomials because I have pivots in the first two columns. Each column corresponds to a polynomial. We have a similar question right here. Okay, so I have a set of 3 polynomials. The question is whether they're dependent or not. So I create the matrix where each column corresponds to the scalar, to the coefficients in the polynomial. So 1, 2, negative 1. The first column corresponds to the first polynomial. 3, 5, 2. The second column corresponds to the second polynomial, and then 5, 5, 7, 0. As you can see, I don't have a term x squared here. That means that x squared in this polynomial, in this quadratic polynomial, is multiplied by 0. And now we row reduce. 1, 3, 5. 2 minus 2 is 0. 5 minus 6 is negative 1. 7 minus 10 is negative 3. Negative 1 plus 1 is 0. 2 plus 3 is 5, and 0 plus 5 is 5. I multiply the second row by, not that I have to, but I multiply the second row by negative 1, 0, 1, 3, and I divide the last row by 5, so 0, 1, 1, and I get 1, 3, 5, 0, 1, 3, 0, 1, sorry, 0, 0. Now I subtract these two rows, negative 2. So since I get pivot in each column, that means that all of these 3 polynomials are linearly independent. Which means that the basis of the span of this set is basically these 3 polynomials, because they're independent. And I do something similar with this question. Now this is the question whether these 3 matrices are independent. Just by looking at this set, I can see that the second matrix is just a constant multiple of the first matrix, right? And we know that 2 vectors are linearly dependent if they're scalar multiples of each other, so these 2 are linearly dependent. I can do the same idea by checking whether this is dependent with this vector, so I have to multiply 1 by 3 to get 3, but if I multiply 2 by 3 I don't get 4, so these two are not scalar multiples. So these two are linearly independent, and then the basis for the span of S3 is going to be consisted of these two vectors, of these two 2 by 2 matrices. If the question was not as easy, then we create again a matrix where the first column is going to correspond to the first vector. Doesn't matter how you're gonna plug these entries in the column, as long as you keep the order consistent for each vector. So I'm gonna go 1 2 1 3, 1 2 1 3. That means 2 4 2 6, and then 3 4 5 7. Okay, and now you row reduce this and you will get the matrix 1 2 0 0 0 1 0 0 0 0 0 0. I don't have a pivot in the in all the columns. That means that they're linearly dependent. Indeed, I have that the second column is just twice the first column, exactly what we conclude by observing these matrices. And I have a pivot in the first column and in the last column, which means that the first matrix and the third matrix are linearly independent, and they create the basis for the span of S.